Okay, so welcome back. This is lecture 2. In yesterday's lecture, we introduced the notion of a limit by just looking at examples, graphing functions, and then calculating numerically the behavior of a function as the input approaches some value. And the general idea was that the function is moving towards something, right? It's getting arbitrarily close to something. In fact, I should probably just write that down from last time. So the idea from last time is that some function f of x becomes arbitrarily close to a single number L as x approaches some value c, and then like in parentheses from either side. Right, so this was like the idea that we were exploring, and when there was a single number that the function was approaching as x approaches some value c, we wrote that down as limit as x approaches c, f of x equals to L. So that's what we wrote. Now, this is not a formal definition. This is kind of like an idea that we were exploring. At the beginning of this lecture, we're going to actually write down the formal definition. Okay, so as with many things in mathematics, there's the intuition, but then there's also the formality that's needed to have, like, I don't know, stable footing in thinking about the concept. So here's the formal definition. Okay, so let me make sure I'm not differing from the textbook too much. Okay, all right, so let f be defined on some open interval containing C. Okay. So we write limit as x approaches C, f of x equals L whenever. So there's a little bit of technicality here. I'll explain after I write it down more in detail. I'll explain more in detail after I write it down. Okay, whenever for every epsilon greater than 0, there exists a delta greater than 0, so that the absolute value of x minus c less than delta implies the absolute value of f of x minus L is less than epsilon. So this part right here is the formal definition. So that and that are the same thing. So if this happens, then we can write that. And if this is the case, then this must be true. So I'm not assuming that any of you have taken discrete math yet and learned the rules of logic, but inside of this statement, there is what are called quantifiers and conditional statements. So what do I mean by that? A quantifier is saying basically for every, or there exists, these are the two types of quantifiers that you'll learn about in the discrete math course. So, and what it's trying to say is that for every literally means that any possible epsilon greater than 0. So epsilon is just some number, right? There must exist this delta greater than 0 so that this conditional statement here holds. This implies this. Okay, still it's probably a little hazy about what's going on. So let's take a pause and kind of look at these pieces here, right? So when you look at this absolute value, what are you thinking? Like f of x minus L in absolute value. What comes to mind? Like, I mentioned this last lecture. What does the absolute value tell us?
Distance.
It's distance. So we have to think about this in terms of distance, right? So let's read it out loud again, now with distance. So for every epsilon greater than 0, there is a number delta greater than 0, so that the distance from x to c less than delta implies the distance from f of x minus L is less than epsilon. So again, this is distance. How far away is f of x to L? Does that make sense? Like, just maybe I should like actually take a moment to recall this notion. The absolute value of A minus B is the distance from A to B. And from B to A, it's the same thing. So, for example, like the absolute value of 4 minus 6. So the absolute value of 4 minus 6 is the absolute value of -2, which is just 2. And if you look at a number line, 0, 1, 2, 3, 4, 5, 6, like that. So here's 4. And here's 6. How many units are between them? 1, 2. It's the distance from 4 to 6. That's the absolute value of the difference. So with that, we can kind of think more about what this definition is saying. So I'm going to need a lot of room here. So suppose we have some function with a limit L. Okay, we're assuming that to be true. Like suppose, and I can just draw it like, I don't know. So this is a piecewise function called f. And the limit here, I can just tell graphically looking, so if this is like c right here, I can just tell graphically that this will be the limit L. Okay, now let's see that this function and that limit L satisfies this definition. It's going to. So, okay, so for every epsilon, there's a delta. Okay, so what does this mean? Pick any epsilon that you want. So epsilon could be like, I don't know, 0.5 or something. That's a positive number, okay? And then I don't know what delta is going to be, but I can pick my epsilon. And what I know, as soon as I have an epsilon, I know that there is a distance from F to L that's at most epsilon. So if I add epsilon to L, I get like here. That's like L plus epsilon. And if I subtract epsilon, that's like L minus epsilon. So what I'm doing here is basically creating a little interval around L, right? So any number inside of here, right, is within distance epsilon to L. Okay? Now, what this definition is saying is that there has to exist a delta that's kind of bounding around C. So I don't know what delta is, but say maybe there. So this is like C plus delta, C minus delta right there. And then I see that anything inside of there is within distance delta to C. Right? Any x I pick inside of there is going to satisfy this part right here. So, okay, let's look at this conditional now. Pick any x that makes this true. Okay, so I can pick any x I want to inside of here. Like x not maybe. Subscript not 0. It satisfies this. So then this definition says this must also be satisfied. So like right there, that's f at that x that we picked. And you see that it's inside of there. Okay? And this is true for any x that we pick inside this interval here. So if I picked another x, like right there, call it like x1, there's like f at x3. In fact, anything I pick inside of here, anything is going to be mapped to something inside of there. Okay? But that was just like one example of this size epsilon. But this definition here states that it has to be true for every single possible epsilon. So I could pick, I don't know, maybe epsilon equal to like 0.000001 or something. So then I would have a really small little interval around L. This definition, if it holds for this function, which it does, implies there has to exist another delta. So there's going to be some interval around here so that everything gets mapped here. Everything gets mapped there. So this is the idea of formalizing what we were doing last time with this definition. And I apologize, my cat is like meowing at me a lot. So, this is how it's presented in your textbook. And you'll open it up and you'll see that you'll have these like intervals here that are mapped inside of there. I personally think that that can be a little bit confusing. So let me draw another picture for you to help kind of nail down this, this notion. So in this blob right here, we have real numbers. And then in this blob over here, we also have real numbers. Now, this is a Cartesian plane, but really what a Cartesian plane is, the real number line crossed with the real number line. You pick a real number and you get another real number. Yeah. Here, 1 second. Okay. All right. So, all right, we have real numbers mapped to real numbers. That's what functions do. They take in something here and they spit out something over here. So suppose we have a function f. Takes in real numbers, spits out real numbers. It's really the same concept. Real number, you get another real number. That's what the function does. And suppose, like, here's L, and then like over here, here is like C. Okay? And we're supposing that this function converges to L as x approaches to C. So pick an epsilon, and then make a little ball around that L. So you agree that like, so this is like the radius of this circle. So if I pick any point in there, its distance to L is less than epsilon. What this definition is saying is that as soon as I pick an epsilon, I get a delta around C, so that anything I pick inside of here must get mapped inside of there. That's the notion of this definition. Okay, but this was just like one epsilon. What about we pick a smaller one? Okay. Well, I can pick a really small epsilon around L and draw my little ball around it. If this definition holds, it means that there has to be a delta around C so that everything in here gets sent over here. Right, I pick an epsilon, there must be a delta so that if something is in that ball, it must get mapped inside of that ball there. Now, I find it easier to think about this picture than that, but they're really the same thing. Like for example, with the first delta that we picked, like you can think about it like this is like a ball, and then this is another ball. Everything inside here gets sent to something inside there. Same concept. And the reason why this is special is that this epsilon can be as small as we want. So we can just make a tiny, tiny ball here. We're guaranteed, if that limit exists, that there's always a ball around here that everything in there gets sent over here, no matter how small it is. So that's the formal definition of the limit. Now, it might be special to maybe look at what we can derive from this formal definition. Okay, so let's look at if this makes any sense for the following limit theorems. So maybe some basic limit properties. So one. So actually, I need to write out a little bit more. Let B and C be real numbers. And N be a positive integer. That's basically like a counting number. 1, 2, 3, 4, so forth. That's what integers are, positive integers. So the limit as x approaches c, b is equal to b. So that's just a constant function. 2. Limit as x approaches c of x is equal to c. And 3. Limit as x approaches c of x to the power n is equal to c to the power. Okay. So let's see if we can verify one of these properties. I don't know. So this is what the textbook tells us. This is what the formal definition is. So if that's true, it better satisfy this. We better be able to somehow prove it. So maybe let's consider 2. Okay, so what does the graph look like for 2? So our function is f of x equals to x. So that looks like this. Okay. And then let's pick any c, maybe right there. And the claim is that this limit is going to be equal to c. So, okay. I hate to do this formality to you, but I think you need to at least see it once. So let epsilon be greater than 0. And choose delta equal to epsilon. Then the absolute value, so then if x minus c in absolute value, if the distance from x to c is less than delta, then, so maybe I might jumbling this up really bad right now. So if distance from x to c is less than delta, then the distance from f of x to c is less than epsilon. So it does satisfy this definition. Now you might not see it immediately, but it's not hard to see if you just start here and work your way out. So we pick, so here, here's c plus epsilon, here's c minus epsilon, and we picked delta to be equal to epsilon in this case. So c plus delta, c minus delta, and we just pick any x in there, okay? Any x we want to, that one. So we know that that x that we picked satisfies that. But we know something else. Delta is the same thing as epsilon, right? So we know that x minus c, the distance, is at most epsilon. But what is f? I mean, what is x? X is equal to f of x. So we immediately get f of x, which is that, minus c is less than epsilon. And c here, that's like our L. So we picked an x in there, and it must be the case that this holds. The idea is that, we just basically, well, not basically, we proved this limit formula here. And we proved it by choosing an arbitrary epsilon and then finding a delta so that this works for any epsilon that we pick. no matter what epsilon we pick, if we just set delta equal to epsilon, in this case, we get that this holds. So we've like verified that. Okay. So yeah, this is technically a proof. But we're not going to be too concerned with proofs in this course. I just thought I would show you that we can write that because we can find a delta and epsilon to make this always work. We can find a delta for any epsilon to make this work in that specific case. Okay, so you can use these now. I'm just going to go ahead and say that all of these proofs are basically just verifying that with a similar type of argument. These are formulas that you can use. Some other properties now. And there's a big list of them. So we still have B and C are real numbers, n is a positive integer. So next, assume limits as x approaches C of f of x equals to L, and the limit as x approaches C g of x equals n. Or I don't know, your book uses k, I'll use k. So 1, 2, 3. So next property 4. The limit as x approaches C of f of x times g of x is equal to L times k. Okay. 5. Limit as x approaches C of B times f of x is equal to B times L. Okay. Six, the limit as x approaches C of f of x plus or minus, depending on the context, g of x is equal to L plus or minus m. So limits distribute over sums and also over differences. Okay. And 7, limit as x approaches C of f of x divided by g of x equals L over m, provided m is not equal to 0. And finally, limit as x approaches C, f of x to the power n is equal to L. All right. All right, so here's our list of all the basic rules. And from these rules, we can easily calculate limits in a more direct manner. In our previous lecture, we were kind of playing with the idea, playing with the functions, numerically approximating what the limit should be. With these rules, we can directly calculate. However, it's important to remember that when calculating limits, these are processes, right? This is a process. Where is that function going as x goes there? And where is this product going as x goes to C? Okay. So let's look at some examples. Find limit as x approaches 2 of 4x squared plus 3. And so, yes, you can graphically look at this and numerically look at this, but with these rules, we can kind of just go ahead and straightforward calculate it algebraically in a sense. Okay, so limit as x approaches 2, x squared plus 3. We know by this property here that we can distribute the limit over the sum. So this would be the limit as x approaches 2 of 4x squared plus limit as x approaches 2 of the constant 3. Okay. Now we know from this property here that the scalars can be like almost in a sense factored out. So here we can take that 4 out. And then finally, that is just x to the power 2. So we know that this limit is going to be just 2 squared. So 4. 4 times 4 is 16. And then the limit of a constant is just a constant from the first rule that I wrote down. And then we get that this is 19. Okay. And maybe let me give you an example problem to work with. Let's say find, pick a random example out of the book. The limit as x approaches 1 of 2x cubed minus 6x plus 5. Okay, I'm going to go ahead and pause the recording and give you a chance to work on that on your own. Okay, so let's look at the solution. Okay, so here's my limit. Okay, so we know that limits distribute over sums and differences, so we can write this as 3 limits. And then finally, plus, I'm running out of room, but the limit of a constant is just a constant, right? So I'm just going to put that constant there. I already know the limit there. Also, to be very careful when you have numbers that aren't associated with this limit here, it might help to put brackets around there. So you know that limit's being applied there, and that 5 is just a constant. So then we can take out these constants here. So take out that 2, take out the 6. Okay. And then finally, these are simple limits to value now. This would be just 1 cubed. This will just be 1, so minus 6 plus the 5, and that's equal to 1. Okay. Okay. So next up, we have a theorem. Okay. Okay, so this is actually a really useful one. So if P of X is a polynomial, and C is a real number, then the limits as X approaches C, P of X is just equal to P evaluated at C. Okay, so now here we could, with this becomes even easier. We don't have to split it up or anything because that's a polynomial, right? So this theorem is telling us that, oh, in order to evaluate that limit, we could have just plugged in 1 and then immediately got into here without using these steps. However, it is important to know about these steps for other types of problems because not everything is a simple polynomial. Okay, and then there's another part to this. More. If, let's say, Q of X is a polynomial with Q of C not equal to 0, then the limit as X approaches C, P of X divided by Q of X is equal to Q of C over Q of C. So this is a rational function now. So an example of how to apply that rational version, we could use maybe like, I don't know, limit as X approaches 2 of X squared minus 1 all over X plus 2. That's a rational function. So this will be what? This 4 squared minus 1 over 2 plus 2. What is that? 15 over 4. Okay. And that's just applying this theorem here. And we can apply it because the numerator is a polynomial, the denominator is a polynomial. We can just plug in the limiting value C, which in this case was a 2. Okay. All right, so here now.
Wait, Professor, how did you get 15?
4 squared is 16 minus 1.
And where did you get the 4 from?
The 2 plus 2. I basically just put in 2 there and there.
No, I'm sorry. The 4 on top.
Sorry, you're right. This would be a 2.
Oh.
I squared it in my head before putting it in there.
Okay.
So what is that? 4, what says 3/4. Sorry. Thank you. Good little catch there. All right, so next theorem. So let n be a positive integer. Again, whenever I say positive integer, it's like a counting number, like 1, 2, 3, 4, 5, something like that. Then, so the limit below, which I'll write in a moment, is valid all C when n is odd and is valid for C greater than 0 when n is even. And that's this limit here. Limit as x approaches C of the nth root of x is equal to the nth root of C. So when n is odd, you're fine with taking limits on nth roots. When n is even, you have to be careful so that C is greater than 0. And the reason for that is we're avoiding imaginary numbers. Because if n was even and C was negative, then this wouldn't be defined as a real number. Okay. What else? So I sometimes avoid giving this one, but I'm going to go ahead and do it just in case. So if f and g are functions, with, let's say, the limit as x approaches to C of g of x, if that's equal to L, and the limit as x approaches L of f of x is equal to L, then the limit of f composed with g of x as x approaches C is equal to f of L. Now there's a lot in the statement of this theorem, but it's not difficult to see. Actually, no, I was looking at it and there's something wrong with it, like that. So we're assuming that g approaches L as x approaches C, and the limit of f as x approaches L is equal to f of L. So really what's happening here, okay, there's like an intermediate step between here and here. So this really is saying this. And what does this equal? Inside, that's L. That's what we're assuming up here. And that's how that equation is formed. Okay. It's just a theorem on composites. Okay. Next up, one more theorem, or not one more. We're covering a lot of theorems today, but all of these theorems are just tools that you will use to calculate the basic limits. In fact, I don't even want to write this one down. Gotta be careful on how I write this. There's a bunch of them. I'll just say this. Limits as x approaches C, sine of x is equal to sine of C. And the same for all the basic trig functions. So like the limit as x approaches c of cosine of x is just cosine of c. The limit as x approaches c of cotangent of x is just cotangent of x, so forth and so on. Okay, so there's a bunch of these lists, and it might help when you're doing the homework or even like on the exam, the first or the midterm, to have like a sheet of all these rules. So let's see. It's already 1:22. Let's go ahead and take a 15-minute break now. Okay. So during the break, I was thinking that maybe I should like illustrate a use case of this theorem because it's kind of it reads kind of jumbly, but I think an example will illustrate it better. So before moving to the next part of this lecture, I want to give an example of this theorem. Okay, so here we have a limit that we need to find, and we can notice that, okay, this, you can think of this as like a composite function, right? This is a composite. So for example, so if f of x is equal to the cube root of x, and g of x is equal to 2x squared minus 10, then this right here is precisely f composed with g of x, right? So we can think of that expression as this function. Okay, so let's see if it satisfies the hypothesis of this theorem, which is the if statement. So hypothesis is the if, after the then is the conclusion. So okay, let's look at the limit of g of x as x approaches 3. So g of x is 2x squared minus 10, or 2x squared minus 10. So what does this equal? This is a polynomial. We can just plug in the limiting value. So 3 squared is 9, times 2 is 18, right? Minus 10 is 8. Okay? So then that's the limit as x approaches 3 for this thing here. Okay? Now let's look at the limit as x approaches this value for f of x. So limit as x approaches 8, because that's like the L here, right? Of f of x I put an 8 there, just x. So this is a rational function with odd power, or not rational. So this is an odd root, so we can just plug in that 8. So the cube root of 8 is 2. Okay. And that does indeed equal f of, like if I put in a 2 right there, I mean, not a 2, if I put in an 8 right there, I get a 2. So that and that are true, so this must be true. So what this is saying now is that this right here is like f of, so what is this? That 2 there is f of L. At 8. So that must by this theorem, b equal to f of L, which is 2. Okay. So that's true, and that's true, so this must be true. And that's the answer. Okay. Just a quick illustration of this theorem. All right. Next theorem. So in the previous list that I've given you in this lecture, we've learned about evaluating limits of simple functions like polynomials, constants, rational functions, composite functions. Those rules, or those theorems, together with this theorem, give you a lot of room to calculate more general function limits. Okay, so why is that? Okay, so if f of x and g of x are functions so that f of x equals g of x for all x not equal to c on some open interval containing c, and the limit as x approaches c of g of x equals L, then the limit as x approaches c of f of x also equals L. Okay. So one way of interpreting this theorem is that if you have two functions which only differ at one point in some interval, and you know the limit of one of them, you know the limit of the other. So for example, find limit as x approaches 1 of x squared minus 1 over x minus 1. Okay. Now we cannot use the rational limit theorem that I listed, because if I try to take the limit up here and down there, I get a 0 in the denominator. So I can't use that. But I can use this. And the reason for that being is that, so x squared minus 1 over x minus 1 is equal to x minus 1 times x plus 1 all over x minus 1, which is just equal to x minus 1 divided by x minus 1 is just 1. We're left with x plus 1. So f of x is equal to our original statement here. We can just define that way. And then g of x is equal to x plus 1. These two functions agree at every point except for x equals to 1. And I'll draw the graph for you so you can see that. So Next is 0 at 1. Next is 0. So this is the graph of f(x). This function is defined everywhere except for x equals to 1. This is the graph of g of x. These are two functions that are defined everywhere, and they differ at 1. They don't match up here. But they're basically the same function, with the exception of that one point, that one input value. So the limit of this function as x approaches 1, it's just a simple polynomial. We know the answer to that limit. It's 2. Right, it's just right there. This theorem now tells us that since they only differ at 1 point, we know the limit here as well. It has to be the same as that function. So we know the answer. It's 2. Okay. So this is actually a very useful theorem because we know a lot of limit rules for basic type of functions. If we encounter something that isn't one of those basic functions, then if we can somehow like reduce it to maybe a different function that differs from that one at 1 point, then we can find this limit as well, just by applying our other limit properties. Okay. All right. Now, I would call, maybe I'll give this a name. Like when you have a rational function like this and you can't like directly evaluate the limit, then I noticed that I factored and divided out one of the terms, one of the factors. So I would call this like maybe like, I don't know, the divide out technique. Okay. But there are other techniques that you need to know about. For example, find maybe the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. Okay, so if we try to evaluate this limit directly by just plugging in the limiting value, we get 0 over 0. This is what's called the indeterminate form. So we can't do that. However, if we can algebraically manipulate this to look different but stay the same, we might be able to then use one of these previous limit rules to calculate this limit. So what we can do is we're going to rationalize the statement. This is called like the rationalized technique. Okay. So let's look at our limit here. Okay. Now we can always multiply by 1, right? Multiplying an expression by 1 doesn't change anything. So what we're going to do is we're going to multiply this by a fancy version of 1. And we're going to do this with the goal of removing the radicals. And it's a really simple technique. If you have like radical minus number or other radical, and you want to get rid of them, just multiply in the following way. All right. Hopefully you agree that's 1, right? That divided by itself, it's just the number 1. So this multiplication on this limit is not going to change anything. However, we have it's like a minus b times a plus b. What happens is that, well, you'll see. So we have root x plus 1 times root x plus 1. What's that equal to? Root x plus 1 times root x plus 1. What is that equal to?
X plus 1.
Yeah, it's x plus 1. And then we have root x plus 1 times 1 plus negative 1 times x plus 1, root x plus 1. You see that, right? Like, well, maybe I'll just write it out to be extremely clear. So using the distributive law, that times that, plus that times that, plus that times that. Finally, plus that times that. And then in the denominator, we don't really have to do much. Okay, so what does this end up equaling? Well, the limit is still there. But now, okay, in the numerator, notice this term here. And that term there, they add to 0, right? It's the same thing. So in the numerator, I'll have x plus 1 minus 1, which is just x. X divided by x is just 1. And now we can directly evaluate this limit. We haven't changed anything, right? We just multiplied by 1. So now, if I just plug in a 0 now for x, what do I get? 1 over root 1 plus 1. So if you just plug in now, what you can do, there's no problems there. That's the limit. Okay. All right. So I think that this is a good place to stop the recording.